Good morning. Welcome to our first session of the day. Very exciting. Thank you all for coming. If you're here to find out what AWS Lambda and DynamoDB can do in your serverless applications, you come to the right place. And if you're here to find out how they're using serverless and AWS Lambda and DynamoDB at CapitalOne, you've come to the right place again. My name is Edin Zulic, and I'm a Solutions Director at AWS. I'm really excited to have Srini Palapati with me, who is the Vice President of Consumer Bank Engineering at CapitalOne. My biggest challenge for this session was shrinking the content down to make it fit in the time that we have. So here's what I have. So first, you'll want to hear what DynamoDB is really good at. Then we'll get into how to do things with AWS Lambda and DynamoDB. We'll go into how to implement transactional behavior as well as enable querying in serverless microservices. And then we'll talk about ingesting high-volume time series data with Kinesis, AWS Lambda, and DynamoDB. After that, Srini will take over to talk about serverless at CapitalOne and what he and his team have been doing with AWS Lambda and DynamoDB, how they're creating new services for their customers and run them reliably at scale. AWS Serverless Platform is much more than just function as a service. It includes services and capabilities that enable you to build sophisticated applications and run them at scale. DynamoDB is one of these services, and in fact, it's the only database service in the AWS Serverless Platform. So these are the characteristics that your applications can benefit in your serverless applications can benefit from. So let's see how DynamoDB delivers on these. No server management. DynamoDB is a fully managed service. There is no servers or clusters to manage. Flexible scaling. DynamoDB, especially now with auto-scaling, a new feature that was released earlier this year, provides an easy way to scale your capacity for the load that it needs. And high availability and durability are built in. In fact, DynamoDB is a zero downtime service. It's designed to run 24/7, 365. And finally, when it comes to idle capacity, that's where DynamoDB still has some work to do. However, with some of the new features, such as auto-scaling, that gap is really being closed as well. So auto-scaling, in addition to increasing the capacity to meet your load, also decreases the capacity when your load goes down, which helps reduce that idle capacity. So I'm sure you already know what DynamoDB is. But I want to share one example of what it does, as that's a great way to describe what it really is. Prime Day this year, DynamoDB served over 3 trillion requests from all Amazon.com sites, Alexa, and Amazon fulfillment centers. And all this with the same consistent performance and high availability. So talk about a mission-critical service. So DynamoDB is designed to be used as an operational database in OLTP use cases, where you know access patterns, and you can design your data model to support those access patterns. And that's really important to remember about DynamoDB. Also, DynamoDB is designed for applications that need scale, performance, high availability, and reliability. In other words, DynamoDB is designed for mission-critical applications. So these are some of the things that your applications can benefit from just by using DynamoDB. Some of the common use cases here include shopping cart and sessions, two of the original use cases that required at Amazon that required the kind of scale and performance that the traditional databases at the time just could not deliver. So let's take a look at building blocks that we use for these use cases. This is what I call a basic building block for serverless microservices. And it's a pattern that's used in many use cases, including mobile backend, web applications, or e-commerce applications. So DynamoDB's low latency both for reads and writes, so in single-digit milliseconds, as well as the fact that it's API-driven, so there's no need for object relational mapping, make it well suited for use in AWS Lambda functions. So in addition to the ability to store your data, operational data, in DynamoDB and access it quickly, you can stream those data to consumers that might then do some post-processing, downstream processing, or enable different materialized views for various kinds of queries. And this is enabled by DynamoDB streams, which is basically a feature that's a transaction log tailing mechanism that reliably delivers all updates to your data downstream. Now, those updates, when you use DynamoDB streams with Lambda, and they're really well integrated, then just show up in your Lambda function invocation as events that you then do whatever you need to do with. And so this enables us to segregate our operational database and still be able to stream data and enable querying, basically for whatever requirements that we might have on the querying side. And this enables us to enable these querying without ever having to change the data model in our operational database. So one, core building block, API gateway, Lambda, and DynamoDB. And then the second building block that I want to point out is the building block for reliable event delivery, which is made up of DynamoDB streams and Lambda. So let's take a quick look under the hood of DynamoDB streams and see how it works with Dynamo on one side and then your Lambda functions on the other. Now, streams consist of shards, and shards are there to enable scaling. However, streams are fully managed. And so, unlike with Kinesis streams, there's nothing for you to do with those shards. So, the way it works is DynamoDB table, as you probably know, stores data in partitions. For each active partition, there's an active shard in the DynamoDB stream that's attached for that table. And then on the other side of that, for each shard, there's an instance of your AWS Lambda function. So DynamoDB streams takes care of managing your data in the stream and providing the data exactly once in a strictly ordered fashion based on the item key. The stream is durable and it's scalable, so as you add partitions to your, or as DynamoDB rather, adds partitions to your DynamoDB table, the stream that's attached to the table also adds the shards to be able to also scale accordingly. The data is retained for 24 hours and then it's deleted without you having to do anything about it. And since DynamoDB streams is an event source for AWS Lambda, you simply consume events from the stream by basically taking the event passed into your Lambda handler function. Now, the way this works, Lambda pulls the stream up to 4 times a second if it needs to, and then synchronously invokes your function. Now, this is important to note because it will keep retrying until it succeeds. And this is related to the guarantee of ordered, strictly by key order delivery. So you're guaranteed that your data will be delivered in order, and that Lambda will execute on it in the same order. So DynamoDB streams and Lambda provides a reliable at least once event delivery. So you say, this is great, but DynamoDB is no SQL database. I need SQL. When we looked at how we were using our existing databases at Amazon, we found out that in many cases, we weren't using relational databases for their relational capabilities. The access pattern, a lot of times, was key value based. Now, that said, there are plenty of use cases where SQL is called for. However, in many OLTP applications, a non-relational database is more than adequate. In fact, it can deliver better performance and scale. So let's take a look at an example where we use microservices for an e-commerce application. We'll first compare relational versus non-relational data model, and then we'll look into implementing transactional behavior as well as enabling querying in distributed microservices architecture. So let's consider 3 microservices. And since these are microservices, each one gets its own database. And of course, each database is bound by the same business context that the microservice is bound by. And so, for example, in the case of shopping cart service, our data model might simply consist of the cart and cart item. And if we're using our serverless platform at AWS to do all this, we'll be using API Gateway, AWS Lambda, and Amazon DynamoDB. Let's take a look at how we can model our shopping cart and compare what that looks like in a relational versus non-relational database. So in a relational database, we're likely to have a couple of tables, one for the cart, one for the cart items. And an update would be a transaction that includes both tables. By contrast, in a non-relational database, we can put all the data for the shopping cart in a single item in a single table. Non-relational database, in this case DynamoDB, have a flexible schema. So the schema is still there. The relations are still there too, but we use a different approach. We use aggregate orientation to store data in a non-relational database. What that means is that we're storing our data in aggregates. And in this particular case, the aggregate is the shopping cart. Aggregate is a collection of data or objects that are used and therefore stored together. And that really allows us to simply have really good performance both for reads and writes, and also implement atomic updates to our shopping cart. So on one side, normalized schema, where we use what we use in a relational database, and then on the other, denormalized schema, where we use aggregates to store data. Let's see how we go about updating a cart in DynamoDB. We use an approach that's based on optimistic concurrency control, which means we first read data, we modify the data, and then update the data in the database, but only if it has not been updated since we read it. And the way we ensure that in DynamoDB is by using condition expression in either our put item or update item operation. So in this case, the condition expression we're using for this example takes the last update timestamp. And so we'll compare the timestamp that we read with the timestamp at the time of update, and if they match, it means that nothing else updated the data in the meantime. This allows us to ensure data consistency using basically conditional put or conditional update in DynamoDB. So that's great, you say, but then how do we do transaction that might span microservices? So in this case, a traditional approach might be to use something like a two-phase commit. And first part, we do checkout and then inventory update in the product catalog service. Well, here, we'd like to see how we can do this without blocking. So without any locking involved. And we can do that as an eventually consistent sequence of steps in which each step is transactional with respect to its own shopping cart service. So in our case, the first step would be the checkout, and then the second step would be inventory update. The key to doing this correctly is making sure that any updates to the database, in our case to the cart table, are also reliably or atomically published for downstream consumption by the product catalog service. And we do that, so we can do that a couple of different ways. One approach is to use event sourcing. Another approach is to use database transaction log tailing. Well, guess what? DynamoDB Streams is exactly that. It's a transaction log tailing mechanism, and that's exactly what we're going to use. So here, we initiate the checkout by using maybe a dedicated attribute and setting the checkout attribute to true. That's published downstream by DynamoDB Streams and then consumed by the Lambda, which belongs to the product catalog service. Now that Lambda is triggered by this attribute checkout set to true, and then it invokes the API on the product catalog service to update the product catalog and reserve the items in the shopping cart. And if it all goes well, this Lambda will invoke a commit API on the shopping cart service, which will then signal the end of the transaction. Now, both these operations have to be idempotent, and that's one thing we should remember. So then, this pattern is known as a Saga pattern, and in this case, we're implementing Saga pattern using DynamoDB streams and Lambda. So in case there is a failure, let's say that one of the products is out of stock, and we can't reserve it for our shopping cart. Our shopping cart service has to have a compensating action available so that we can do a rollback. So in this case, we would invoke the rollback API on the cart service. And in our example, that API will simply set our checkout flag in our shopping cart item to false, to mark that the transaction has been aborted, basically. And the shopping cart data is still in the table. The transaction has ended in a rollback, but everything is consistent in the end. This is the list of update items for this particular use case. So add, remove item, checkout, begin, checkout, commit, checkout, rollback. You'll notice that each one uses the same optimistic concurrency control approach that consists of reading the item and then updating the item based on the last update timestamp and then the additional checkout condition. I have to mention another building block for transactions, and that's the step functions service. Step functions make it easier to implement more complex workflows, and it can actually be combined with the approach that we just went over, so the approach that uses DynamoDB streams and Lambda. For example, you could start with the streams-based approach, and then if the next step in the transaction is more involved, simply implement that step using step functions. And in this case, Lambda functions have to be idempotent as well. And, but step functions is really a good way of making sure that all your steps work together as a state machine, and it provides observability into your workflow. So to recap real quick, we just went over how to implement transactions using DynamoDB and Lambda. And the building blocks for that were DynamoDB streams, Lambda, and also step functions. One thing about this approach is that it can increase the total latency of the transaction because it involves constructs that are asynchronous and eventually consistent, such as DynamoDB streams. Next, let's talk a little bit about querying microservices architectures. There are some challenges when it comes to querying in microservices, right? We have all these different microservices and they all own their own data. That's one. Two, operational view of data does not necessarily satisfy the needs that we might have for our queries. And also, if we would like to implement support for new queries in the system, we'd like to be able to do that without having to mess with the model of our operational database. The solution is to separate the operational and querying views. And this is where polyglot persistence really comes into play. It enables you, this solution enables you to use the right database for the right job. And that's command query responsibility segregation pattern. Now you already remember this slide, and we talked about this earlier, and how DynamoDB streams and AWS Lambda enable reliable streaming of your data from your operational database. And that's exactly what we can do to implement CQRS in this context. So we have reliable downstream delivery of events from your operational database. This really allows you to optimize your operational database for the use cases that it needs to support, and also optimize your querying use cases for their own needs. And guess what? They also get to be scalable independently from each other. That's the command query responsibility segregation. Now, each one of those querying services could be exposed as a microservice. If you have several of those, you won't be able to just use DynamoDB streams as a pub-sub mechanism. It's not designed for that. DynamoDB streams is designed to just make those updates available. But if you need a pub-sub mechanism, you have to use some kind of a fanning approach. One way to do that is by using a Lambda fan-out function and then fan the data out to different consumers. Another approach that we see being used more and more relies on Amazon Kinesis streams to do the fan-out. What's nice about using Kinesis for this is that it preserves the same ordering if you need that. The second thing is it provides a little bit more decoupling because the stream is accessible via its endpoint ARN. And so some takeaways for querying and enabling querying with microservices. CQRS provides separation of concerns. I think of it as the single responsibility principle applied at the architectural level, right? We're segregating responsibilities and optimizing subsystems basically to do what they're designed to do best. Each side is independently scalable, and we can expose each query as a microservice. Now, we all know that with microservices, we already have to deal with that added complexity because they're now distributed and so on, so nothing new there. And the latency, we have to be tolerant to possible just larger or longer latency. Next, I'd like to talk about ingesting high-volume time series data. So what we need is high-volume ingest. Let's say we're talking about 100,000 data points per second. But we would also like to access data for a number of days, maybe even months, by sensor ID and time range. So in this case, we're talking about sensor data and then being able to access those data in a very short access time, under 10 milliseconds. So given the scale and access requirements, we need to use the services that are designed for this. Amazon Kinesis Streams is designed to enable large-scale, large-volume ingest of data. We'll use AWS Lambda to get the events from Kinesis and then to store them in DynamoDB. Now, why are we using DynamoDB here? We're accessing data on a per-sensor basis, and DynamoDB is really good at that. And in fact, we're accessing by sensor ID and time range, and we can organize our schema in DynamoDB to really match that use case very well by selecting the partition key to be the sensor ID and by making the timestamp the sort key. This allows us to do quick queries on, give me the range of data for this sensor between time A and time B. And this is very efficient millisecond latency access because DynamoDB, based on our keys, will store related data for the same sensor together. And solutions architecture for this might look like this. We're using CloudWatch to monitor our services and possibly also to implement automatic scaling for our Kinesis streams. Lambda and DynamoDB can scale automatically. Now, for DynamoDB, I should say that as long as your changes in volume are gradual, DynamoDB is designed to accommodate the scale-out of gradually changing workload. But for example, if you add a large number of sensors at the same time, you might have to use explicit update table API to increase the capacity of your DynamoDB table. So streams are here because we're using the time to live feature in DynamoDB to expire data after the time that we don't need it anymore. So TTL, you can think of it as an expiration date on items in a grocery store, except with DynamoDB, when that item expires, it's automatically removed from the shelf by DynamoDB. And within 48 hours, in fact, that's the time frame on that. Now, the data that's expired, we can actually stream and archive in S3 using Kinesis Firehose. And again, we're using streams in AWS Lambda to do that. Now, to access data in DynamoDB, you'll notice that I'm not using that building block of API gateway here. I just simply wanted to show a different approach. You can access data directly from DynamoDB using many different client APIs. In this case, I'm using JavaScript, and I'm using Cognito to authenticate my client before accessing data in DynamoDB. So every good solution should be cost optimized to avoid unnecessary cost. Main input data into our cost calculation here is the data rate, 100,000 data points per second, and data storage. And let's talk about 1 month's worth of data storage, which I calculated to be about 2.5 terabytes if each data point is about 50 bytes. Let's estimate some cost here. Lambda will come out to about $2,000 to $5,000 per month. There's more than one way to calculate, and then you can change the maximum batch size. And so depending on the batch size, as well as the memory size of your Lambda function, that all kind of factors into the cost calculation. For Kinesis, 100,000 records, pretty straightforward. You need at least 100 shards, because a single Kinesis shard can handle 1,000 requests per second. That comes out to $5,000 a month. Now, DynamoDB, if I use a single write for each data point that I have, I'm going to need 100,000 write capacity units of DynamoDB. That'll come out to $50,000 a month. That's a significant cost for DynamoDB. So where is the problem here? If we look at the pricing model for DynamoDB, one write capacity unit is 1 kilobyte. But in our scenario, we're storing data points that are about, let's say, 50 bytes in size. So our write capacity utilization for write is less than 5%. Now that reminds me of my gym membership. I pay for the whole month and I use about 5% of it. But let's see what we can do about this. So in our architecture, batches of data are delivered from Kinesis to our Lambda function. So when we invoke that function, we have a number of events, multiple events for multiple sensors. How about if we just group events for each sensor and store them in a single item? So if I'm dealing with temperature readings, it could be anything, and these metrics could be even more complex. I could simply group multiple metrics into a single DynamoDB item and use one DynamoDB write capacity unit instead of 16 in this case. And so we're grouping multiple data points into a single item. That can save us on writes. Now, there is no reason why we could not compress data that we store in DynamoDB. And we have many customers who do that too. So in this case, since we're accessing data based on ID and this attribute called DT, which is timestamp, the data attribute that contains our metrics could simply be compressed. And so we can increase our storage efficiency and save even more on writes. And we're also managing lifetime of data in DynamoDB using TTL. Speaking of which, TTL is used by designating an attribute to be an expiration timestamp, and it's on a per item basis. So in our case, we could configure this TTL and set it on each record, for example, in our Lambda function. In fact, we could even use environment variables to pass our TTL value, the lifetime duration of our data, into our Lambda function as an environment variable. And then Lambda function, the other Lambda function that's used in the TTL mechanism. So if we'd like to archive our data into S3, we can create a Lambda function that can detect items that are deleted by TTL in the stream, and then maybe use Kinesis Firehose to store them in S3. So if we look at the cost here, we see that we can store items efficiently by grouping them in DynamoDB, and we can save 10x on cost. And we can even use compression to save even more. A little bit about scaling considerations. If we're adding more sensors, for Kinesis you have to add more shards. Lambda and DynamoDB scale automatically, and DynamoDB auto-scaling enables that. Now, if you're adding more events per sensor, Lambda function will simply create denser DynamoDB items. It'll end up storing more data points in each item. Monitoring, very important. I listed what I think are fairly important metrics to consider for your production use cases. And then some takeaways, finally. For DynamoDB, it's very important to know your data, know the structure, how big are my data items, access patterns, and know the cost model. And based on that, you can optimize your architecture, your solution. Now, in our case, the optimizations that we used were binning, storing multiple data points in a single item, compression, TTL to delete cold data, and then queue-based load leveling for uneven workload patterns. Now, that's what we can use Kinesis for. For Lambda, it's important to reuse database connections by creating your clients to DynamoDB outside the Lambda handler function. And then test for optimal batch size and memory, CPU, and execution time. And finally, monitoring is critical for any production application. With that, my part of the talk is done, and I'd like to turn it over to Srini.
Much, Aiden, for sharing such important details about serverless architectures on DynamoDB. Hello everyone, my name is Srini Uppalapati. I'm a vice president at the Consumer Bank engineering team within CapitalOne. And I'm here today to share with you the journey me and my teams have taken in basically moving millions of customers' financial transactions from a large monolith mainframe system into the cloud with a lean towards serverless architectures. CapitalOne is one of the 10 largest banks within the United States. We serve approximately 45 million customer accounts, and we offer a range of financial products, from credit cards, checking and savings accounts, small business accounts, consumer bank accounts, and auto finance accounts. And we also have investing platform, and the team is based in Seattle. The consumer bank engineering team is spread across multiple sites. I have engineering teams spread between New York office, Wilmington office, McLean, and Richmond. And as I mentioned, we also have an investing wing in Seattle. Traditionally, the retail bank has always been powered by a large monolith mainframe system. When I talk about a monolith mainframe system, think of it as a bank in a box. The mainframe system has customer information, account information, the ledger, taxes, statements, the whole 9 yards around providing banking services for our customers. When you think about the various service channels through which our customers service their accounts, mobile, web, and the branches, they end up integrating with our modern RESTful API platform on which CapitalOne has invested heavily in the recent years. We have a full API lifecycle management, our own internal API gateway, and an external gateway to expose our APIs to merchants as well as developers. These set of modern RESTful APIs end up integrating with our legacy SOAP layer, and this SOAP layer in turn integrates with the mainframe system for reading and writing information. In a nutshell, this high-level architecture is pretty much consistent for many large financial institutions across the whole world. About a decade ago, this architecture worked fine. But now, with the advent of cloud and all the modern DevOps infrastructure available to us, there are some significant challenges that we're starting to face with this architecture. In the last few years, CapitalOne has invested heavily on our mobile platform, both iOS and Android. And we have launched an industry best rated banking app, and our customers love it. We see a steady adoption of mobile traffic on both the platforms, and that to new customers servicing their accounts on their mobile channel. Basically, in the next few slides, I'm going to set up the context as to why we embarked on the journey of building this transactions hub in the cloud. At CapitalOne, I also have the good fortune of collaboratively working with a brilliant product team. Both tech and product are collaborating to come up with innovative financial digital experiences for our customers, and majority of them are dependent on relying critical financial data like transactions and accounts, which are boxed in the monolith mainframe system. With CapitalOne taking advantage of the AWS services, many of our RESTful APIs and some of our front-end applications are continuously deployed into production round the clock. In some cases, we deploy hundreds of applications each month, leveraging the robust DevOps infrastructure and our CI/CD pipelines. When you look at the traditional mainframe system, they still aligned to the waterfall methodology of moving software from one environment to the environment, depending on large amounts of manual regression testing. And if you think about it, it's largely because of how much kludgy dependency and features we have within the monolith system. And then suddenly we have a clash of the newer infrastructure versus the old, impacting our ability to ship product faster into the hands of our customers. During holiday season, like Thanksgiving and Christmas, we also see a steady increase in traffic. And with the legacy architecture, we are starting to see slow response times for our critical services. There have been instances of reliability because of lack of resiliency. And the only way out was to throw more money at the mainframe system to basically remediate these challenges. So a combination of new traffic, large amounts of traffic, and our inability to scale and be resilient, and on top of that, making the data available in the modern infrastructure to build new digital experiences collectively basically enticed us to solve this problem by taking advantage of the serverless architecture. There are a few things that we said. So when you think about a mainframe system, where do we start? Given the intricate dependencies and so many data, so where exactly do we start? On closer analysis, we figured out that 80% of the traffic is all garnered towards reading customers' financial transactions. The same transactional data is extremely critical for the new digital products that we are building. And hence, that gave us the focus to prioritize to tackle the read traffic problem for customers' transactional data. So if you look at the challenges that the team was faced with, first and foremost, we had to bootstrap 18 months of transactional data for audit and compliance reasons for each account, which translates to billions of customers' transactions, and make it available in the cloud. And we choose DynamoDB as our data store. We also had to put in place a near real-time messaging infrastructure to keep the transactions in sync between the mainframe and the data in DynamoDB. It was also very critical that we actually handle the data from an encryption and security perspective, because we are talking about customers' sensitive financial transactional data. And then finally, we had to build the new version of the Get Transactions API in the cloud that integrates with DynamoDB API and presents the transactions in a consistent format across all the channels. And then needless to say, the consistency of data was extremely important as we look to cache and sync data between mainframe and DynamoDB. So how did we go about trying to solve these challenges? We put together a top-notch cross-functional engineering team and empowered them to solve for certain data-driven facts around how we declared success criteria for Transaction Hub. First and foremost, the speed. The new service must perform much better than the legacy system. And then the second thing is data integrity. We could not afford to lose any of our transactions in the new system. And then it was very, very important to ensure that the customer's financial transactions were secure. So we ended up adopting the CQRS pattern, the command query responsibility segregation implementation. And I know Aiden touched about it, the same pattern in a few slides ago. Basically, we are talking about two data models, one for writes and one for reads. As the customers continue to deposit their checks, tap their phones at point of sale, or swipe their debit cards, all those transactions end up streaming into the mainframe system. And then we will have a near real-time infrastructure to keep those transactions in sync in DynamoDB. And the goal of this entire initiative was to migrate all of the read traffic that was hitting the mainframe system, consuming a lot of MIPS and CPU cycles, which were quite costly proposition for CapitalOne, and then move it to DynamoDB. I'm going to walk through the high-level logical architecture diagram for this Transaction Hub ecosystem, starting with the batch, and then followed by the near real-time messaging infrastructure. On the mainframe system, we have a COBOL program which actually reads millions of transactions and puts them in files and transmits them through our internal gateway and seamlessly, securely FTPs them into the S3 bucket where all the files are fully encrypted. The moment the file arrives on the S3 bucket, an SNS notification gets relayed, and there is a Lambda function which is subscribing to that SNS notification, and that Lambda function connects to an RDS database and basically inserts the state of the file, indicating that the file has arrived. We have a CloudWatch rule which triggers a second Lambda function which looks at the state of the RDS function and basically spins up a new EC2 instance on which we have a Spring Batch application running. This Spring Batch application connects to the S3 bucket, parses the transactions, encrypts each transaction, and inserts them into DynamoDB. If you realize, DynamoDB as of today does not support encryption at rest, so we end up taking advantage of the custom DynamoDB encryption libraries, and in conjunction with the KMS keys, which are region-based, we encrypt each transactional record and then ingest that transactional record into DynamoDB. We then have the new version of the GetTransactions API running on an EC2 instance in front of our own CapitalOne API gateway, and this new version of the API is made available to all our channels, and we end up serving the transactional data consistently across all our channels. We also have a near real-time messaging infrastructure which basically keeps the mainframe transactions and the transactions in DynamoDB in sync. In this case, we are taking advantage of an existing IBM MQ messaging infrastructure, and for resiliency purposes, we have 4 queue managers. And then on the EC2 instance, we have a Spring Boot application which is listening to the transactional events which are being relayed via the messaging infrastructure. And then the Spring Boot application reads the transactions, encrypts the transactions, and again inserts them into DynamoDB. So you can see that through a combination of Lambda functions and messaging infrastructure, we have support for both batch and real-time to keep data in sync in our CQRS pattern. This slide demonstrates a list of all AWS services we have used in the Transaction Hub ecosystem. And I would also like to add one specific Lambda function we have in place, which is to dynamically provision, read and write throughput settings on DynamoDB based on our usage patterns, and we are able to affect cost savings for CapitalOne, again through a Lambda function. Within CapitalOne, we have a lot of rigor when it comes to operational and business monitoring, and those aspects are firmly baked into the doneness criteria of every product we build and ship into the hands of the customers. I'm pleased to announce that the entire Transaction Hub ecosystem is live in production for the last several months and serving millions of transactions for our customers. And the new API and the Transaction Hub ecosystem has an average response time of 50 milliseconds. And what you are looking at is our production New Relic dashboard. And we also use, in some cases, Nagios for operational monitoring for the Transaction Hub ecosystem. In CapitalOne, for this initiative, we leverage Elasticsearch in conjunction with Logstash and Kibana dashboards for business monitoring. What you are looking at on the left-hand side is the Kibana dashboards for all batch ingestion. You can see that every day we are able to successfully read and ingest millions of transactions in the batch mode in approximately 40 minutes, and having the ability to dial up the provision capacity units and bring down the time by which we can catch up. On the right-hand side, you're seeing the number of transactional events on a given day by hour. We are able to read via the MQ infrastructure and ingest seamlessly into DynamoDB. It is also fantastic insight for our business because we can now see the peak volume hours on a given 24-hour period, during which we will need to accordingly provision the appropriate throughput settings to meet our needs of catching up DynamoDB. As we are live with Transactions Hub, we are now looking to expand this architecture to also cache account-related information, and this time we are iteratively and progressively leaning towards more serverless components. In the first logical architecture diagram a few slides ago, I demonstrated that we had a Spring Batch application running on EC2 instance. Right now, my team is actually gutting down that entire infrastructure and instead replacing it with 3-step functions. one at the batch level, one at the file level, and one at a smaller chunk level, and then using these step functions to orchestrate multiple Lambda functions to seamlessly read and ingest millions of account-related information into DynamoDB. Again, bringing in efficiencies around speed to market and also bringing in cost savings relative to the EC2-based infrastructure. In the next few slides, I'm going to touch upon 3 specific business use cases within CapitalOne where we have built upon the transaction hub to meet our consumer needs. The first use case is around sending out statement email notifications, statement-ready email notifications for our customers. The second use case is where we are now incrementally starting to move some of our APIs, which are running on EC2 instances, into Lambda functions and making it available for our channels. And the third use case is a new product and a feature called Second Look, which our card customers already enjoy, where we are again leveraging DynamoDB streams in conjunction with data in DynamoDB and Lambda functions to actually implement that feature. So this is the high-level logical architecture diagram for how we are managing to send statement-ready email notifications to millions of our customers. As it stands today, we have a legacy data warehouse and a Control-M batch program that is manually kicked off to send off these email notifications to our customers. And there is a manual review process to verify these statements. What we are now doing in production is to replace that infrastructure with a seamless Lambda function that actually reads the percentage allocation of customers to which we have to send the email alerts at a particular cycle date. And at the same time, this Lambda function reads data of all the customer information from S3 bucket, and it juxtaposes the appropriate email templates and basically creates an S3 file. And we have an email communication application that processes this S3 file and sends emails to millions of our customers, indicating to them that the statements are ready for them to view on the digital channels. As you can see, this entire infrastructure has been stood up both on East and West regions for resiliency purposes. Again, one other great use case of where we are tearing down a legacy data warehouse infrastructure and instead replacing that with serverless and Lambda to meet the needs of our business. This is a specific use case where we are actually exposing our get statements API, which traditionally used to be running on an EC2 instance, instead to be replaced by a Lambda function. This particular API actually provides the PDF statements back to the various digital channels, and now we are replacing that with a Lambda function. So you can see that any request pertaining to get statements coming from our mobile and web comes through a WAF layer for security purposes. And once it crosses the WAF layer, we have our own orchestration layer within the CapitalOne VPC. Then we have our own API gateway within CapitalOne VPC, which authenticates the requests coming in from valid client applications, in this case, the orchestration layer. Once the gateway actually authenticates the request, it is then able to seamlessly route the request to the Lambda function. And this is again giving more opportunities for our engineers and products to build appropriate business APIs as Lambda functions and securely expose them by onboarding them onto our internal gateway to our various channels. Second Look. Today, we've had this feature in production for our card customers for a long time, where round the clock we do account level monitoring, and then we are looking for duplicate transactions and automated renewal subscription fees from certain vendors and merchants, and proactively alerting our customers through our mobile app through email. We are now working with our product to make the same feature available to our debit card customers, but this time taking advantage of DynamoDB streams and Lambda functions in a true serverless architecture. So we have transactional data already available in DynamoDB, and we are now enabling DynamoDB streams, and we are streaming tens and millions of transactional events through the DynamoDB stream. We have a Lambda function which inspects the transactions in the DynamoDB stream and identifies new transactions that are streaming in. And then it hands it over to a second Lambda function which inspects the transaction for duplicate transactions and unwanted subscription fees for our customers and sends email notifications. Again, one other fantastic use case of enabling serverless architectures to meet the needs of our customers. There are various lessons that we have learned in our journey of migrating customers' transactional data from a mainframe system to DynamoDB in the cloud, and I'll touch upon a few of them. It is very, very important to know your data. The initial files that we got from the source system were all coming through primary keys from the mainframe system, and this was creating a lot of hot partition issues and throttling errors in production. And we had to basically ensure that the data was distributed so that the data was actually being ingested in parallel partitions at the same time to avoid the hard partition problem. It is very, very important to test at scale. We did not notice the hard partition issue in production in the lower environments, and we only identified it in production at large volumes. And it becomes very, very critical that you actually test your use cases in the lower environments so that you're not faced with a similar situation. Know your access patterns upfront. What I mean by that is once you actually create your indexes and tables and ingest the data, and you then try to identify your patterns, you cannot have the opportunity to change the keys, and you'll basically be forced to re-ingest the data. So you will be served good by knowing what your access patterns are so that you can design your indexes and your tables appropriately. VPC-based endpoints. So few months ago, the endpoint of DynamoDB was actually a public-faced endpoint. Now, what that really meant was, for security purposes, the request from CapitalOne had to go through a proxy layer. Now, thanks to the collaborative effort between CapitalOne and the DynamoDB team, now it is available as a VPC-based endpoint. We were able to avoid the additional hop through a proxy layer, and we are now seeing significant improvement in performance time, approximately around 20% both for reads and writes, by skipping the additional proxy layer. I already touched upon the fact that today DynamoDB does not support encryption at rest. And our way of working around that situation is by leveraging region-based KMS keys, and again, working with the DynamoDB team to take advantage of the client encryption libraries to custom encrypt each transactional record and then securely save it in DynamoDB. That brings an end to the entire presentation. I have two announcements to make. First one, CapitalOne has a booth at the Expo Center. I would encourage you guys to please stop by so that we can share more fantastic use cases of how we are leveraging AWS in our technological strategy and digital transformation journey within CapitalOne. The second announcement is CapitalOne is contributing and creating an open source project called Cloud Custodian, which basically helps organizations to better manage their AWS environments when it comes to security policies, tagging policies, and cost management. All day Tuesday, the DevExchange team in CapitalOne is available to interact with the entire user community team. You will get an opportunity to talk face-to-face with the developers behind the Cloud Custodian product. I would encourage you guys to please stop at the Encore and take advantage of that all day Tuesday. Now, finally, it's a humbling experience to stand in front of you and share the fantastic work that me and my teams have done. And I want to thank each one of you for the time and the opportunity. And I will turn this over to Erin to say the closing comments.
Thank you, Srini.
Thank you.
Thanks very much. We appreciate your feedback. Check out what's new in DynamoDB this Wednesday, 3:15, and Veronese 24:05. Thanks again.
Thank you.
I will stick around for questions after this. I will stick around and take any questions off the stage. Thank you.